Okay, this is a picture of what is on the whiteboard, and it is a summary of everything you are going to need to do your lab write-up, and that means the calculations. So as you can see up here, this is A1, this is A2, A3, and A4. You are going to be calculating the percent error for each of these parts of the lab. So let's start with part A. And specifically, let's talk about part A1. Okay, so you measured the volume of water, and what you were doing was filling each of the vessels to the 10 milliliter mark. And then in part A2 through 4, you used the 15, 25, and 20 milliliters of water. So let's start by looking at A1. So make sure that you label everything you are going to do, and I'm going to do one example for you. And so the one that I will do is the 10 milliliter graduated cylinder. And I'm going to mark that that is what I am calculating. So right here on your data table is the 10 milliliter graduated cylinder. And what you're going to do is you are going to use only the difference column when you are calculating percent error. And this difference column is going to be your actual or your accepted value. So I'm going to just write the word accepted, but we'll just say that's the true value. That's the real value that we were trying to reach. And what happened in our lab is that we thought we were putting in 10 milliliters. And so we're going to call that the experimental. Okay. And it was on the first slide, but just to refresh your memory, percent error, which is a measure of how accurate a reading is the experimental minus the accepted divided by the accepted times 100. So here, I'm going to write it out. So the experimental is what we thought. So it's 10 milliliters. The accepted is the true value, which is right here. Okay? And in this case, it was 11.89. Divide that by, as it says in the formula, the accepted, which again is 11.89. And then multiply that by 100, and that gives you your percent. Now, I will say that this is an absolute value, so if you come up with a negative number, all you just have to do is change the sign to positive because it's an absolute value. So 10 minus 11.89 equals, divided by 11.89 equals, times 100 equals. And so this group had, for their error, 15.9% error. Okay. So that is for the 10 milliliter graduated cylinder. That's the first. And so you'll do this 2 more times. You'll do it for the 100 milliliter graduated cylinder and the 50 milliliter beaker. And both times the experimental will equal 10 milliliters as it did up above, and your accepted will be the difference readings for these two. So far what you have done then, if you have calculated, is you have done this first part of the calculations. So now let's look at the second part. And one of the things that you have to understand is that in this part of the lab, you were adding volume each time. So A2 was 15 milliliters. And then in A3, it was the original 15 plus 25. And in A4, it was the original 15 plus 25 plus 20. And so each of those will be the experimental values. So for A2, it's going to be 15. For A3, it's going to be 40. And for A4, it is going to be 60 because that was the total volume added. So that is for the experimental values. Now, in A2 through 4, the accepted or true values will be the mass of the flask with water minus the empty flask, because that will give you the mass of water. So let's do an example. So going back to our data table, I am going to look at the, first I'm going to start with the burette. I'll do that one. So for the burette, the difference is 15 milliliters, okay? And so we said that that is our experimental. And remember the formula for percent error is experimental minus accepted divided by accepted times 100. It's an absolute value, so it's always positive, and this is percent error. Okay? Now, so for the burette, I'm going to label that in this section. So burette, or A2, and I am going to put my experimental, which is 15, and then I'm going to figure out what my accepted is. And like I said on the previous slide, accepted is this number minus the empty flask. So in this case, it is going to be 92.6 minus 77.6. And so then for these other two, you'll do the same thing when you're trying to figure out the accepted. So what we're saying is whatever the balance read was the true value. So when I do that, I get exactly 15. That's interesting. That means they had a 0% error, because 15 minus 15 divided by 15 is going to be 0% error. And that is your ultimate goal. So all of them will not end up like that. But the thing that I want to remind you when you are calculating these, first is the burette, then is the pipette, and then is the graduated cylinder, the 100 milliliter graduated cylinder. And for those, the experimental is what we thought we were adding. So in the burette, it was 15 milliliters, which we just did. And the pipette will be 40 milliliters. And after adding the water from the graduated cylinder, it will be 60 milliliters. So those numbers are your experimental. And then subtracting the balance reading with the water, subtract from that the empty flask, and that gives you your accepted. So then after you're done doing those percent error calculations, I want you to write a little paragraph, and all I want you to talk about is why we used the burette in A1 and the balance in A2, A3, and A4 as our true values. Why did we choose those? How could better true values be obtained? Is there a relationship between the accuracy of the measurement and the diameter of the instruments? In other words, compare the burette with the graduated cylinder. Is one of them narrower than the other? Does that mean it's more accurate? So remember that lower percent error means more accurate. Now, in part B, all I want you to do is calculate the average or the means of the readings. So you're going to add your difference column together, all together, add all five, and then divide by 5, and that gives you your average.